Hi guys, here's the second related rates problem, and this one is a cone problem. So here it is. A conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is the water being poured into the cup when the water level is 8 centimeters? So first, just like the last example, I'm going to go through and I'm going to circle any words that tell me I'm dealing with a rate. So a conical paper cup, 10 centimeters tall, radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate, so there's my first rate, of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? Okay, so they're telling me the rate of change of the height of the water, and they're asking me what's the rate of change of the amount of water that's being poured into the cup. So the amount of water in the cup, how fast is that? At what rate is that water increasing? So this might take some thinking, but this rate is going to be the rate of change of the amount of water in the cup. That is the volume of the water in the cup. Okay, so we know the rate of change of the height of the water in the cup, and we want to know what the rate of change of the volume of the water in the cup is. Okay, and these two rates are related because the volume of the volume of a cone depends on the height of the cone. Okay, so now using this template, solving a related rates problem. And like I said in the last video, if you didn't see it, I said that I'm going to give you guys one of these to use on the test. It's optional though whether you use it or not. So first draw a picture of the situation, but don't label the picture with any numbers, okay? Because the danger here, why I don't want you to label with numbers yet, is because you only want to label the picture with constants. And yeah, some of these things some of these numbers they're giving us these dimensions are not constant dimensions, and we don't want to make the mistake of labeling the picture with them. So we have a cone that is a paper cup. There's water in it, okay? That's going to be the radius of the cup, but then the water itself forms like a smaller cone inside of the paper cup, so that will also have a radius. And then if you go like that, this is the height of the paper cup. There's the height of the water that's inside of it. Okay, to solve this problem, we need to write an equation. To figure out the equation, identify the concept from the box below that is relevant to this problem. Now, there could be more than one concept. So I know I'm dealing with volume because I'm dealing with the amount of water that is in this cup. That would be the volume of the water. And then also, if you look carefully, guys, this is a triangle, and this is another triangle. So we also have similar triangles. So I'm going to be able to write down two formulas here. Okay, so we've got V equals, and I'll give you this on the test, pi over 3 r squared h. That's the volume of a cone. And, okay, I'm going to jump to C. Oh, okay, maybe I should do this now. All right, so now C. Label the picture with any constant dimensions you were given. So back to this, the paper cup, this is constant here. The conical paper cup, it's 10 centimeters tall. The cup is not changing. It's just the water inside of it whose height would be changing, but the cup is always going to be 10 centimeters tall. And then the radius of the cup is 10 centimeters as well, and that is not going to change. Okay, so there's that. That was part C. Label the picture with any constant, I underlined constant, dimensions that were given. Part D, label the picture with the variables in the equation. So the variables are V, R, and H. V don't bother, but R and H, we can label those. So this is the radius of the water. That is the height of the water. This formula is going to give us the volume of the water. Okay, now so I've written my volume formula, but I haven't yet written my similar triangles formula. So I'll do that off to the side. When you've got similar triangles, guys, you can set up a proportion. And you can set it up a number of ways. I'm going to set it up, I'm going to go I'll go R over R, I'll go R over 10 equals H over 10. But actually, when I did this earlier, I did R over H equals 10 over 10. That's another way you could set up the proportion. So, but I'll do it this way. I'll say R over 10 equals H over 10. And when I picked this problem, I didn't see right away that it would work out so nicely. But, guys, this is going to give us that R equals H. Okay, so that's pretty nice right there. That's usually not going to happen, all right? But this probably is not going to happen on your test. So make sure you practice those problems that I gave you where this doesn't happen. Okay, so label the picture. So we just did part D. Part E, the charts below are intended to outline the logic involved in solving a related rates problem. Fill them out. Okay, so the possible rates, what is changing? So look at your formulas and ask yourself which variables are changing. We've got volume, radius, height. Are they all changing over time? The answer is yes. As water's being poured in here, these are all changing. The volume's changing. The radius is changing. The height is changing. Not at the same rate, but, you know, those are the rates that are involved. So the possible rates that I'm working with are V prime, R prime, and H prime. And I wrote this last year. I said possible. I mean, these are definitely rates of change because these things are changing. But I think I said possible because, you know, we're not really clear on maybe at the outset of the problem how we're going to use these. Known rates. Okay, so back to the problem. I circled the word rate here. The cup is being filled with water so that the water level, that would be the height of the water, rises at a rate of 2 centimeters per second. So this rate is the rate of change of the height of the water. So the known rate is that H prime is 2. And then the rate to find, at what rate is water being poured into the cup when the water level is 8 centimeters. So this is the rate of change of the volume. Right, that's the rate of change of the amount of water in the cup. So that's going to be V prime. And then at what moment when the water level is 8 centimeters. So the water level is the height, and that's going to be 8 centimeters. Okay, any other known values? No, not at the moment. Are they constant? The reason I ask this is because you substitute constants before differentiating, but you substitute everything else after. I've got no constants for the water that are going in here. All right. So now so part F is to differentiate the equation or equations you wrote, remembering that every variable is a function of time, so everything's implicit, everything chain rule. So I'll take the derivative of this. So we've got V prime equals, I need product rule here. I'm going to look at that as one function, and I'll look at that as another. So derivative of the first function is pi over 3, I'll bring down the pi over 3, 2r implicit, so r prime. And then bring down the h plus, bring down the first function, pi over 3, r squared, and then derivative of h is h prime. Okay. And then I'll take the derivative of this equation also. If you write down more than one equation, take the derivative of both of them. So if r equals h, then r prime equals h prime. All right, that one is pretty simple. Now guys, let me make an observation over here, because I'm going to be substituting into this equation, and I see r's, I see r, I see h, I see r prime, I see h prime. I know h prime and h. Okay, I know h prime, and I know h at the moment that I care about. But I'm also going to need to have values for r and r prime. So now I'm going to go over here, and I'm going to do some thinking. I'm going to say when h equals 8, well, since r and h are equal, r equals 8. I'll say so. And then I'll say, and when h prime equals 2, because that's what we know, r prime equals 2. All right, so this is going to be valuable because the final step is to substitute where appropriate to solve the problem. So where appropriate means everywhere except for what you're solving for. So I'm solving for v prime, so that's going to stay as it was. And you might not do this, which is fine, but I'm going to set up a blank underneath everything I'm substituting in for. I put the 2 out in front there. So blank under r prime, blank under h, bring down the plus sign. Pi over 3, blank squared. And you might not find this necessary, but it may help you if you're ever like stuck. You know, to just set up blanks first and then think through like what could go in to that blank. Okay, what's going in for r? Well, off to the side, I have that r is 8, so 8's going in. What's going in for r prime? 2. What's going in for h? Also 8. Guys, this won't happen too often where r and h are the same, but it's happening here. What's going in for r? Again, 8. What's going in for h prime? 2. Okay, and then just plug that into your calculator, and I'm about to write the final answer. And guys, the problems we've done so far, you usually have been solving for r prime or h prime, which is a little more complicated than what I'm doing now. So yeah, definitely practice the problems that I gave for you to practice. So now I'll say when h equals 8 centimeters, this is centimeters, yep. V prime equals, I already did this earlier, 402.1239. And volume is 3 dimensions, so it's going to be centimeters cubed per second in this case. Okay, so there's that, guys. I hope that this is shedding some light on how to do these problems. I know that they were, you know, I kind of sprung them on you fast, but hopefully this helps. All right, see you soon.